Here's a couple of problems that I typically give on my test 2 for Calculus 1. I'm giving you a description of a graph and you draw a graph. So I'm testing on how you visualize the effects of taking derivatives or second derivatives. So let's start. This is the problem number 8. I'm going to do 2 of these examples. I start with f is a continuous function on the interval 0 to 5, closed interval 0 to 5. So there are no breaks in the graph. Now, I shouldn't have to say that, because if there's no break, if I tell you it's continuous, you ought to know that. But I found too many people getting the question wrong, so I guess I caved in a little bit. F is differentiable on the interval, the open interval 0 to 5, except at x equal to 1. Now that doesn't mean you're going to have a hole at x equal to 1 or an asymptote, because there are no breaks in the graph. How can this be? How can it not be differentiable at a particular number? Well, when it has a sharp point. That's typically when we don't have a derivative at a certain value of x. All right, so I've got those 2 things down. So at x equal to 1, I'll have some sort of a sharp point. I'll keep that in mind when I go and do my graph. Now, let's take a look at some of the requirements of the graph. F double prime of x equals a 0 when x is less than 1. So what kind of functions have the second derivative equal to 0? Well, lines, any kind of a function like y equals mx plus b, if you take its second derivative, you'll get 0. So keep that in mind. The easiest thing to do here is a straight line. There may be some weird cases where you could get, but I don't think so. Yeah, there are some weird situations where you could, but the thing is, keep this in mind. Straight line for this part. So for x less than 1, I'm going to have a straight line. This just means there's no curve. Let's keep that in mind. F prime of x is less than 0 for x less than 1. So that means that we're decreasing for x less than 1. We are no curve for x less than 1, and we're decreasing for x less than 1. So there's nothing here that tells you what y values to use or anything like that. What I'll do then is I've got to start at 0 and go to 5, so I really don't care. The numbers don't matter. I'll put a dot here, and I will do the best I can to draw a straight. That is, believe me, the best I can do on this screen. And then f double prime of x is positive for x greater than 1. So we're going to have concave up when x is greater than 1. And then f prime of x is positive for x greater than 1. So it's an increasing function that is concave up. So for this part from 1 on, I can do this. And this indicates the sharp point I was talking about, and this will cover everything we need. There's no breaks. F is differentiable. Well, you know what I didn't do, though? I didn't make it go all the way to 5. So I should probably take that out. This I can leave in. That's supposed to be a straight line. That's the best I can do. But to get to 5, maybe I can do it like so. Put a dot there at the end of it, and there we go. I've got concave up and increasing, no concavity and decreasing. So that's as easy as these things get. And as long as you have all the features, like I see students do this all the time, because there's no breaks in the graph. I've checked it off. Differentiable on the interval except x equal 1, and I purposely put a sharp point at x equal to 1. And then these are the things that I use to make up the graph. So I think this one was from spring 2017, and this one might be from summer 2017. Let's go ahead and do that one too. In this case, it's continuous on the interval from the closed interval 0 to 4, so there are no breaks in the graph. Differentiable on the interval 0 to 4 except at 1 and 3. You cannot have holes at 1 and 3. Sharp points are more likely what you're going to have at 1 and 3. F prime of 2 equals 0. So I have a flat tangent line there. F has a local maximum at x equal to 1. So maybe it'll have a sharp point there. If I go and put something at 1, if it's a local maximum at x equal to 1, then since it's not differentiable there, I could probably do something like this. I'll change that in a minute, depending on what the rest of the stuff says, but that's the kind of a thing that can happen at 1. F prime of 2 equals 0. So if I'm going to do this, I have to level it off so that the derivative or the tangent line is horizontal there. F has an absolute maximum at 3, and still it's not differentiable there. So we could perhaps do something like this. And then F has an absolute minimum at 4. So something like that will be fine. Let's see if I have everything that it's required. Let me put this here at the beginning. F is continuous on the interval. I've taken care of that. There's no breaks in the graph. F is differentiable on the interval 0 to 4 except at 1 and 3, so not differentiable at 1. It's smooth elsewhere. And it's not differentiable at 3. F prime of 2 equals 0. There it is right there. F has a local maximum at x equal to 1. Yeah, I can see that I did that one. That's there. F has a local minimum at x equal to 2. And yes, I didn't know this in advance. It just happened to work out this way. There it is. There's a local minimum right there. So I'll check that one off. F has an absolute maximum at x equal to 3. 3. There it is. And then F has an absolute minimum at x equal to 4. And there you go. So that's the lowest point on the graph at 4, the highest point on the graph at 3. Now here's a type of graph that asks you to see if you can understand local max and mins plus points of inflection, things like that, by looking at a graph first. So here's the rules that I've set down. I've given you a graph. For each local maximum, put a dot on the graph and label it with a capital M for each local maximum. So that's what I'll do now. I'll put a dot here and I'll put a capital M. Dot here, capital M. Make that dot more. You should make your dots evident to me. Are there any other local maximums? No, remember, you don't count endpoints as local anything. For each local minimum, put a dot on the graph and label it with the letter mu. The reason I choose mu is because it doesn't look nearly as much like M, although I'm beginning to think that students might be able to play this game and make something that is difficult for me to discern. But let me go ahead and put my mu there and put my mu here. See how that kind of is sort of like an M? So I guess if I were a student and concerned if the instructor would understand me, I will try to make my capital M very capital M-ish. For each absolute maximum, put a dot on the graph and label it with the letter A. I don't need a dot. This is the highest point on the graph, so I'll put a capital A above it. The dot's already there for you. For each absolute minimum, put a dot on the graph and label it with the letter alpha. Sometimes you have to use, it's possible that you will use more than one letter at some of the points. So this is one of those cases. I'll put an alpha here because that is my absolute minimum. And then for each inflection point, put a dot on the graph and label it with the letter I. Now you're looking for changes in concavity from concave up to down or vice versa. These you have to estimate, but you can still know that they are somewhere. Like here, you can see right here, it's got a horizontal tangent line here. It's slightly concave up, but then it starts to concave down on us. So if you were to put it, say here, I'm not going to get you for exactitude, but for completely missing out that there's a change in concavity, I will. So there's where, as far as I'm concerned, it's concave down now, concave down, concave down. It still kind of feels concave down until I guess I get around here, almost like it's on the axis. So I guess I would put it somewhere around here and put an I to indicate that. Put a better I to indicate that. Then we're concave up for all concave up, but then right around here, it kind of looks like it's going to go concave down. And then we're concave down, concave down, concave down. And here's another one that feels like it happens right about on the x-axis itself. I'll go ahead and put my eye there. So concave down, and then concave up, concave up. Now, I'll be honest with you. If you miss this slight change in concavity here, I don't think I was taking off any credit, but my eyes are telling me, though, that I'm concave up until right around here. It looks like it actually changes concavity to me. So that's what I'd write. I don't think I took off anything if people missed it or not. I'll try to make it more obvious. And try to make your answers obvious too. So let's see if we've done everything that was asked. For each local maximum, put a dot on the graph and label it with the letter M. So local maximum. I only had 2 of them. Endpoint, it does not count. For each local minimum, use the letter mu. So that doesn't count as a local minimum. That's a local minimum. Remember, it's got to have a graph on both sides of it to determine whether it's a local min or max. Here, this one has a local minimum. Now for an absolute maximum, label it with the letter capital A. There it is. That's the highest point on the graph. Alpha is the absolute min, so I put it over here. These two are, this is both a local minimum and an absolute minimum. And then finally, try to estimate where the eyes should be. The changes in inflection. That's whenever you change from up to down or from down to up.